back to my channel, and today I'm going to be talking about the history of physics. In this video specifically, I'm going to be talking about electromagnetism. On my previous video on the history of physics, I talked about classical mechanics. Classical mechanics is essentially the study of the motion of macroscopic objects. For example, we could calculate the trajectory of a planet orbiting around its star. We could also calculate the motion of a rolling object on planet Earth, like a ball per se. So classical mechanics has a lot of applications and forms a foundation for all the other branches of physics. For example, classical mechanics forms the foundations for essentially electromagnetism, quantum mechanics, general relativity, special relativity, and etc. So classical mechanics is very important. However, when we look at the prerequisites of classical mechanics in terms of mathematics, classical mechanics only involves a mastery of algebra and arithmetic and a good understanding of integral and differential calculus. However, when we start to dive deep into electromagnetism, one needs a very deep and mastery understanding of integral and differential calculus and even a little bit of vector calculus itself. So electromagnetism is a little bit more mathematically intensive. Okay, now that we've talked about classical mechanics and how electromagnetism is a little bit more mathematically intensive than classical mechanics, let's talk about what classical mechanics is. So what is classical mechanics? Okay, to understand classical mechanics, we must understand the theory of everything. So what is the theory of everything? Well, the theory of everything is not the theory of everything. Rather, it's a unification of the four fundamental forces in nature: the strong force, the weak force, which are called nuclear forces, the electromagnetic force, and essentially the gravitational force. The gravitational force is gravity. The strong force is essentially gluons and what holds the atom together. The weak force is essentially radioactivity, and the electromagnetic force is essentially just dealing with the photon. So what is the photon? The photon is the particle representing electromagnetism on the standard model of the particle physics. Well, on the standard model of particle physics, essentially the photon just represents light, or electromagnetic waves. This gives us insight to what electromagnetism is. Electromagnetism studies electromagnetic waves and electricity and magnetism and their intricate relationships. So that's particularly what electromagnetism studies. Let's talk about the founders of electromagnetism. So here are the two founders that we mostly are showing. So for example, we have Michael Faraday and James Clerk Maxwell. There are many other engineers and scientists who developed electromagnetism because it's a very big field. But these two are pretty much the main founders. Michael Faraday was born first, and he had little education, which means he didn't know much mathematics and he didn't know much science. However, he was a big experimenter, and he loved experimentation. So if we think about it, experimentation, when people think about it, is mostly a stereotypical example of a chemist or a biologist working in a laboratory, modifying the genome, or essentially just particularly doing chemical equations and mixing chemical solutions, and so on and so forth. So that's what people think when thinking of experimentation. When thinking of physics and mathematics, they just think of a big blackboard filled with mathematical equations. Rather, it's more physics when they think of a blackboard filled with mathematical equations. So Michael Faraday essentially disproves that stereotype because Michael Faraday had little education, yet he used a lot of experimentation. For example, he showed that if we take a magnet and move it inside a wire, we can generate an electromagnetic field, an electric field. So Michael Faraday essentially kind of established the relationship between magnetism and electricity, electromagnetism itself. So Michael Faraday did many experiments like that, and they were very important to the field of science and electromagnetism. Next, we have James Clerk Maxwell. James Clerk Maxwell was essentially the opposite of Michael Faraday. By the time we have James Clerk Maxwell, electromagnetism developed a little bit more. And by the way, Michael Faraday, when he realized that a magnet moving through a wire essentially generates an electric field or electromagnetic field, this essentially helped create generators. And generators used worldwide today. So we have to thank Michael Faraday for that. Now, if we look at James Clerk Maxwell was the essential opposite of Michael Faraday. Right now, after Michael Faraday was more like, we essentially had a little bit more understanding of electromagnetism. James Clerk Maxwell was a prodigy in mathematics. At the age of 14, he essentially wrote a scientific paper and published it. At the age of 13, he essentially won a mathematics medal. So James Clerk Maxwell was essentially really smart in the field of mathematics. He developed Maxwell's equations and showed and essentially researched a lot, and particularly electromagnetic waves. whereas Michael Faraday particularly worked in electricity and magnetism and their relationships. James Clerk Maxwell worked in electromagnetic waves, showed that light was essentially an electromagnetic wave, and we right now know that we have X-rays, gamma rays, microwave radiation, which we can also consider electromagnetic radiation or electromagnetic waves, and so on and so forth. So James Clerk Maxwell essentially theorized that light is an electromagnetic wave and developed these and formulated particularly these 4 fundamental laws of electromagnetism. Over here we have Gauss's law, which states that the divergence of the electric field is equal to this. The no magnetic monopole rule, which states that the divergence of the magnetic field is equal to 0. Faraday's law, which states that the divergence of the electric field essentially is this. And then we have Ampere-Maxwell law, which says the divergence of the this is the cross product, by the way. The cross product of the electromagnetic field is equal to this. The cross product of H is equal to J plus partial D over partial T. Okay, so as you can see, we have the 4 fundamental laws of electromagnetism. Right now, this doesn't seem that much mathematically intensive. All you can particularly see is probably calculus. That's what most people think. When you see this, you say, oh, okay, we probably just need calculus to solve this. But not just regular calculus. We have a variant form of calculus called vector calculus. To put this into perspective, we have tons of variant forms of calculus. We have multivariable calculus, we have vector calculus, we have tensor calculus. Tensor calculus is used a lot in general relativity, and so on and so forth. We have tons of variant types of calculus. So we have vector calculus over here. One could even arguably say that James Clerk Maxwell was essentially had a specialty in vector calculus. So we can use Maxwell's equations and Maxwell's laws to particularly understand how electric fields and magnetic fields are related and how they flow through different surfaces. Let's just talk about the no magnetic monopole rule, but before that, we say that this is the divergence, this is the curl. If you want to learn more about the divergence, curl, and radiant, which are vector calculus operations, please visit my videos on those vector calculus operations. Okay, I talked about the no magnetic monopole rule on another video on divergence. Let's just have a quick summary over here. So if we have a magnet, we know a magnet has a north and a south pole. So if we just draw vectors going out from the north side and going back in, from going into south side, we can say that this forms an electromagnetic field. And this is what you've seen in pictures. What the no magnetic monopole rule says is that there can't just be a magnet which has a north side and just all the magnetic field just goes out, because it has to come back in. So that's essentially what the divergence of the magnetic field is equal to 0 means. If you want to learn more about that, please visit my video on the divergence. Okay, now that we've talked about that, let's now talk about electromagnetism and its applications in byproducts. So let's talk about byproducts first. Okay, so what are the byproducts of electromagnetism? We have quantum mechanics and we have general relativity. For example, in general relativity, we have Lorentz transformations on the electric field, which is used a lot in special relativity. Along with that, we have electromagnetism and electric fields in the relativistic notation, which is also relativity itself. And Einstein, by the way, he loved electromagnetism because it was such a consistent theory and describes our universe so well. Quantum mechanics, on the other hand, just as I described, involves photons. For example, an electron emitting a photon. And a photon involves electromagnetism. Therefore, as we can see the logic, quantum mechanics uses electromagnetism. And quantum mechanics and general relativity each have byproducts. Well, what are their byproducts? Well, their byproducts form the theory of everything. So what does this mean? Well, the theory of everything, as I described, unifies the 4 fundamental forces. We'll talk about that on the videos about loop quantum gravity and string theory. String theory and loop quantum gravity try to account for our universe to unify these 4 fundamental forces. Remember that they have to account for the electromagnetic force too. So in order to have a complete theory of everything, the theory of everything must have essentially, particularly, must use and have electromagnetism. So we can take a theory of everything and we can use the theory of everything to formulate these equations, or we can use the theory of everything to get the same answer as what happens if we plug stuff into these equations. So that's essentially what the theory of everything should consist of. So a theory of everything is very important. Now let's talk about quantum gravity. quantum gravity, which we'll talk about also in another video, particularly maybe in the history of physics. So quantum gravity is essentially just when we're combining Einstein's theory of general relativity and quantum mechanics itself. Now, if you think about it, electromagnetism is essentially used in quantum mechanics and in general relativity. However, quantum mechanics and general relativity don't mix match. So what it means is maybe electromagnetism is a hidden link between quantum mechanics and general relativity, or maybe it's not. So we have a lot of questions there. Now let's talk about the applications of electromagnetism. Now electromagnetism has tons of applications. Let's think about this, for example. A common problem that high school students face if they're taking AP electromagnetism or AP calculus, no, AP physics C, for example, AP physics C and E&M, AP physics on electricity and magnetism. They might think and they might see, for example, a problem with a circular rod or a vertical rod, and an electric current is passed through it. Find the electric flux or magnetic flux, and so on, or a magnetic field is passed through it. So trying to find the magnetic flux or electric flux, and so on and so forth. So we can use, for example, these problems to gain a better understanding of our world itself. How do we do that? Well, we have to think about how waves propagate, and electric current, how it propagates through essentially different types of materials. For example, we know that wood is an insulator. If we pass, for example, electrons and electricity through particularly a wooden surface, or essentially just a wooden hole or something, then we can see that wood is an insulator, so it can't pass through it. Air is also an insulator, or else we would have tons of currents flying out and getting shocks all the time. So as you can see, we have tons of applications because we can now understand what are conductors, what are insulators, and we can use them a lot. For example, we have semiconductors. These are used a lot in computer science and to make computers. So the computer you have is used from semiconductors, and semiconductors are also made from electricity and magnetism. Also, we can essentially, if we consider a circuit, we can see that in the circuit, how does the energy flow? These also use electromagnetism and have separate equations, but they're product of electromagnetism. So electromagnetism essentially forms electrical engineering. If we have, for example, phones transmit electromagnetic waves. If you're calling someone, the electromagnetic wave travels through a specific place and then goes from there. So electromagnetic waves are all over the place, and electromagnetism popularized them and made them useful so that we can use electromagnetic waves in physics itself for our lives and make our lives easier. Now that we've talked about that, let's summarize. Okay, so we talked about what we talked about in the previous video, classical mechanics, and classical mechanics is a foundation. However, classical mechanics isn't mathematically intensive as electromagnetism. After that, we talked about what electromagnetism is. Electromagnetism is essentially talking about electricity, magnetism, and their intricate relationships, and electromagnetic waves. We also talked about how it relates to the theory of everything. The four fundamental forces, which are electromagnetism, the strong force, the weak force, and the gravitational force. After that, we talked about the two founders of electromagnetism, Michael Faraday, who had little education but contributed a lot to science and popularized experimentation in physics, James Clerk Maxwell, who's a mathematical prodigy and was specialized in vector calculus and formulated over here Maxwell's equations, which are famous for electromagnetism. After that, we essentially talked about a little bit about what mathematics they involve and how mathematically intensive they are. Lastly but not least, we talked about electromagnetism's byproducts in physics itself. And we also talked about electromagnetism's byproducts in technologies. So electromagnetism is essentially very useful and very important. Now that we've talked about that, we can make this video to an end. If you like this video and if you like this channel, please subscribe and learn more. Thank you.